0 to 2 pi, and I can integrate from 0 to 1 in terms of what? In terms of see, because these polar coordinates are based on that circle. Now, the integrand x, right, is what? In terms of x bar, what's x equal to? X bar plus 1, right? But if you put that into our modified polar coordinates, it's what? It's s cosine beta plus 1. And what's my dA? What's dx bar, dy bar? Well, dx bar, dy bar, it's still s ds d beta by our previous arguments in geometry. It has to be the same deal. So the Jacobian, the area element here is s ds d beta. And you see in this choice of coordinates, it's obvious that this integrates to 0 because beta goes full cycle. And we're just left with the one piece. So the answer is pi. I skipped a step, sorry. Integral from 0 to 2 pi 1/2 s squared evaluated from 0 to 1 d beta, which is the integral from 0 to 2 pi of d beta over 2, which is pi. If I take this answer and I divide by pi, what's its significance? Well, I mean, it's equal to 1 for one thing, right? But what is it equal to also? It is the x-coordinate of the centroid. That's one thing that's good. It's the center of mass for the x-coordinate, right? I mean, obviously the center of mass centroid is the center of the circle, right? But I would also point out to you that's the average of x over the circle. It's another thing you could say it is. So these concepts are overlapping, right? It's another classic example I should show you, which is somewhat related to what we're doing. These are good examples. I'm happy about these, yeah. So there's a whole other world of thinking are modified spherical coordinates and modified cylindrical coordinates, right? If your cylinder has x as an axis, then you want to let the cylindrical coordinate be equal to y squared plus z squared, right? So there's sometimes problems where you have to take what we've already done and kind of twist it appropriately for the problem at hand. That's not a segue into what I'm doing. I'm just saying. All right. So here's the example. This is a famous classic example. So calculate the integral. Everybody should see this example in Calculus 3, so since you're part of everybody, I will show it to you. So the integral from minus infinity to infinity of e to the minus ax squared dx. What is that? Now, the problem with calculating that directly is e to the minus x squared is pretty notorious for not having a basic derivative, right? So much so that you'll find statistics books with page after page after page of numbers written for areas under this curve. It's the bell curve, right? And they come up, what's it called? Do you guys remember? I don't remember. I hear, is it the z-score? Is it the, I don't know. I don't remember. I've never taught statistics. I don't know that stuff. But it has deep significance in terms of statistics. Anyway, so here's the idea, is instead of calculating that, we will look at I. We'll derive this in a somewhat circuitous way. We'll take I be the integral over the plane of e to the minus x squared minus y squared dA. So actually, I'm going to basically work it out for a equals to 1, if you don't mind. I mean, if we can work this integral out for a being 1, you can do a simple substitution to get it back for a. Okay, so this is going to be defined to be the limit as a goes to infinity of the double integral over the disk of radius a of e to the minus x squared minus y squared dA. I mean, that's how I'm defining the integral over the plane in terms of larger and larger and larger and larger and larger and larger disks. All right? Yeah, let me erase the a and just, there, fixed. Sorry. That was distracting us. I'm sorry about that. So how would you calculate that? Disk of radius a. Let me draw a picture here. So we have what? We have 0 less than or equal to r less than or equal to a, 0 less than or equal to theta less than or equal to 2 pi. Well, that's an easy. I mean, obviously we want to use polar coordinates, right? So integral from 0 to 2 pi, integral from 0 to a. And here's the awesome thing. In polar coordinates, the dA does what? It gives you a r. And then that's e to the minus r squared dr d theta. So what we couldn't integrate, now we can integrate because we've got the r, right? And the integral is just a u substitution. I mean, the theta integral does what? It goes 2 pi, right? What's the antiderivative of this? It's just 1/2 e to the what? Minus r squared, right? That's not quite right yet because there's a minus, so I have to put a minus 1/2 here as well. Evaluate that from 0 to a. Now, do you guys agree that I put in parentheses is the antiderivative of that? If I differentiate minus 1/2 e to the minus r squared, do I get back r e to the minus r squared? Derivative of the inside function gives you minus 2r. Pretty sure it works, right? Agree, disagree? This step right here, I integrated. The theta I just integrated to 2 pi. Follow that? Bless you. So what we have here is the limit as a goes to infinity of what? Let's see here, minus pi e to the minus a squared plus what? Pi. That's a pretty easy limit to calculate. What happens as a goes to infinity? E to the minus a squared goes to what? 0, right? So this is just pi. So we agree? Do you guys agree with that calculation? I mean, you can look at it and take it for what it's worth. Oh, I'm not done yet. So, was there a question? Should have expected. Let's see here. integral over R2 e to the minus x squared minus y squared dA. Okay, great. Now we could also calculate the same limit in terms of the limit as a goes to infinity over a square, right, of side length a, right? Well, I guess the side lengths would be 2a. I mean, this is, let's say, minus a to a cross minus a to a. So the squares that are symmetric about the origin, they actually have side length 2a in this setup, right? Now that's kind of interesting, right? Because this is the same as what? Minus a to a, minus a to a, e to the minus x squared. What can I can factor, right? Do you agree? I mean, that's just algebra. So what's that equal to? So using the multiply the integral trick, right? Or if you just call this thing j and call this thing j, then this should just be j squared, right? Because they're both j. It's the same integral, just written with y or x, right? So it's just a change of integration variable. It's the same integral. Hey, but we already worked out with polar coordinates that j squared is equal to pi, right? From this. And so what do we find? The integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi. I want to show you guys a little bit more here before we end today. First of all, how do I get that and get an a in there? How would I do that? Oh, I better hurry. How do I get to the integral from minus infinity to infinity of e to the minus ax squared? What would I do? I let u equal to the square root of a times x, right? Assuming a is positive, and that would give me e to the minus u squared, right? And what's my du? Square root of a dx, right? So I have to do du over the square root of a. But that's what? That's 1 over the square root of a times the square root of pi, by what we just did. So the answer is the square root of pi over a, if you have an a there, by this simple u substitution argument. Now I want to do something that's going to blow your mind a little bit. You can differentiate this expression with respect to a. What happens if you take the derivative of this formula with respect to a? Assume that you can pull the derivative inside the integral. Seems reasonable, right? A and x have no dependence, right? What's this? Derivative of e to the minus ax squared with respect to a is what? Minus 2ax, right? Oh, minus 2x, right? Minus 2x e to the minus ax squared dx, right? But what's the other side? What's the derivative of this? A to the minus 1/2, a to the what? Minus 3, so it's minus 1/2, a to the minus 3/2. Let me clean this up a bit. We have the integral from minus infinity to infinity of x e to the minus ax squared dx is equal to that 2 divided to the other side gives me square root of pi over 4, the square root of a, good grief, well, a to the minus 3/2, I'll just write it like that, but there you go. Although you wonder what that means. I'm not sure that's actually valid. Oh, I'm sorry. I let you guys talk me into something. Is that an x or an x squared? What's partial a of minus ax squared? It is minus x squared. There is no, that is not x, that is x squared, and there's no 2 there. It's just minus x squared. You guys talk me into something. So that just gives us a 2. The minus goes away, and that's x squared. That's correct. And you can keep differentiating this and get more and more identities. This technique is known as differentiation under the integral. There's a vast literature on these things. But anyway, I shut up.